everyone, my name is Naji. I'm today talking about action decision networks for visual tracking with deep reinforcement learning. Here's the outline of my presentation. I will first give a little background, just briefly going over different types of learning, deep learning, reinforcement learning, and its elements, policy, value function, model, and what are the approaches to deal with reinforcement learning problems. Then I'll talk about deep reinforcement learning, which is a combination of deep learning and reinforcement learning. Then I'll come to the paper, talk about the proposed method, which is the action-driven object tracking, their problem definition, how they define reinforcement learning settings, how they train the network, which is a three-step work: a supervised learning, a reinforcement learning, and an online adaptation step. And afterwards, I'll show the results. Okay, for the background, different types of learning. So in machine learning, mainly there are three types of learning algorithms: supervised learning, unsupervised learning, and reinforcement learning. So in the supervised learning, the data has labels, and the learning is based on the input-output pairs. However, on the unsupervised learning, we don't have any labeled data, and the training is basically only on the similarity of the input data. Reinforcement learning is an interactive process, and the learning is based on the states, action, and rewards, which needs to be defined based on the problem that we are trying to solve. There are also some other subcategories here, which are semi-supervised and weakly supervised, which lie between the supervised learning and unsupervised learning. In one, we don't have labels for some portion of the data, and in the other, we do have the labels, but labels are noisy and not exactly what we're searching for. So if we want to see what is the deep learning in a nutshell, deep learning is basically a framework for representation learning, which means that given an objective, we want to learn a representation that is required to achieve that objective. And this learning is based on the raw input data. For reinforcement learning. In the reinforcement learning, however, the purpose is a decision making. So we do have an agent that agent makes some actions and affects the environment. So our agent has the capacity to act, and based on the action, it will influence an environment and change the state of that environment, and its success is measured by a reward signal. And the goal of the reinforcement learning is to select actions that maximize the future reward till the end of the episode. Any reinforcement learning object may include one or more of these components: policy, which is nothing but the agent's behavior function; value function, which describes how good each state and action is at a given step; and model, which is the agent's representation of the environment. And based on that, there are different learning models for reinforcement learning: model-free, policy-based, value-based, and some intersection between those, like anchor critics. So policy. As I mentioned before, policy is the agent's behavior, which is basically nothing but a map from state to action. It can be deterministic, which is given a state, deterministically we select the action, or it can be stochastic, which is a conditional probability of, given a state, what is the probability of the actions. Value function. Value function is basically the prediction of future rewards, which means that how much reward will the agent get from action A at a given state S. Q value is one of the widely used value function, which gives the expected total rewards, discounted total rewards till the end of the episode. Meaning that at state S, if the action A is taken under policy pi with a discount factor, this would be the Q value function, which is describing the total value function discounted by a factor of gamma till the end of the episode. Yes, E is basically the expectation, something like that. Model is basically the description of the environment. So model is learned through the experience, can be taught as a proxy of the environment, and can be something like a planner, which is basically planning by, for example, looking ahead tree. For example, here the agent knows a tree for the environment, and it knows that if it takes the action that leads to the right node, it will get it here, what is the reward, what is the state, and so on. So based on the elements that the reinforcement learning has, there are different approaches to deal with solving the reinforcement learning problems. Value-based reinforcement learning problems try to find the optimal value function, which means that they try to find the maximum value achievable under any policy. They don't care about the policy, they just want to optimize the value function. Policy-based reinforcement learning, on the other hand, is directly trying to optimize the policy, which means that they try to find the policy that is achieving the maximum future reward. Model-based is trying to build a model of the environment, and again, plan by having that model. So they're basically, all three of them are solving the same problem with three different approaches. Deep reinforcement learning is the combination of reinforcement learning and deep learning, meaning that the reinforcement learning will define the objective that we want to solve, and the deep learning will give us the mechanism. This is an example of a deep reinforcement learning system, which is here the agent's policy in this figure is modeled by a deep network. So any element of an RL agent, policy, model, or value function, every one of them can be modeled with a deep neural network. Here in this figure, the policy is modeled by a deep neural network. Okay, now I will talk about the proposed method. I will first give a motivation about the current tracking problems and what is the motivation of this work, and then I'll talk about their work. So the motivation in the tracking problem is that in the current and traditional tracking problems, we assume that we have the object location at a frame and we want to find it in the next frame. The current workflows they find some proposals around the object. These proposals can be made by just searching around it with some restrictions saying that 5 pixels, 10 pixels around it, or a neural network can be used to give us these candidates. And then each one of these candidates is going to be examined and determine whether it's object or background. But here in this proposed method, which is taking actions in order to find the object in the frame, as you can see, very less number of proposals has been examined through the learning problem. Here's another example. We know the location of the object in the previous frame. Here is the tracking by detection problems, which are basically searching around the object by different methods and try to find the object in the current frame. And this method here proposes to take a set of actions in order to find the object at the current frame, given the location of the object at the previous frame. So the object tracking here is modeled by selecting sequential actions. And those actions are basically movements or scales of that bounding box that we already have from the previous step. For example, here in this figure, we do have the location here, and this is the next frame. Here are the set of actions that has been taken to find the object in the next frame. 2 rights, 1 up, scale down, right, and stop. Stop here means that we find the object in this current frame, and then this can be an initial step for the next frame, and we follow the same procedure in the next frame as well. Here is another example. This is the object in the current frame, previous frame, current frame, and future frames. Okay, as I mentioned before, for solving a reinforcement learning problem, we need to define state, reward, and action. Here's how they define the reinforcement learning setting. The actions are a set of 11 discrete actions, which are basically the transition moves left, right, twice left, twice right, which is basically twice movement, scale up, scale down, and stop, which is indicator of finding an object. Yeah, as I mentioned, the transition moves are movements in the 4 directionals, and scale changes maintaining the aspect ratio of the bounding box, and the stop, which is basically finding the object. State is defined based on PT and DT, a tuple. PT is basically the image patch, which is a 112 by 112 3-channel RGB image. And action dynamics is basically the history of actions taken at 10 previous steps. We had 11 actions, 10 previous steps will lead to an array of size 110. This is how we find the patch. Phi here is nothing but the pre-processing function that crops the patch from the frame F. And these are the location of the center. X and Y are the location of the center of the patch. W and H are the width and height of that patch. And for transition, for movements, every movement or scaling down or scaling up is basically done by 3% of the size of width and height. So it's somehow relative. Reward function. Reward function is defined based on the intersection over union of the current image patch that we are at the current frame, and the ground truth, which is basically measuring the overlap ratio. So here, if the intersection over union of the patch and the ground truth is above 0.7, we get a positive reward of 1, otherwise minus 1. And here is the proposed action decision network. So here are the number of frames. We are at frame FL right now. We assume that we know the location at FL minus 1. This is going to be the initial step for the current frame. This frame is going to be fed to a neural network and then will lead to 2 vectors. One 11 vector, which is the actions, and the other vector of size 2, which is deciding whether this patch is the object or the background. After an action is taken, then the state, which is basically the location of the patch, will be updated and fed back to the beginning of the network. So this is an iteration right here. The action history will be stored here and then feeds back here, right here, concatenated with the features extracted from the patch. And this is how we start training the network iteratively inside a frame till we find the object in that frame. And at the end, this location will be the initial step for the next frame, and this will go on. So the training step, as I mentioned, has 3 steps. First, a supervised learning. For training a network in a supervised manner, we do need some data, some label data. And this is how they generate the state action pairs, which are basically the label data that they're going to use for training the network as a multi-class classification network. So assume that in each frame, we know the location of the object, which is the ground truth. Randomly, by Gaussian noise, they sampled some patches around the object. Each of those patches will lead to the location of the ground truth by only one action, and they decide what that action is. For example, this patch will lead to the location of the ground truth if we take the right action. And these are going to be the state action pairs. These are the inputs, and the actions are outputs. This is pretty much supervised, and we can train the network.
You have the ground truth, and you take a page and move it yourself artificially.
Yes, randomly.
You know the action.
Yes.
That's the pair.
Yes, that's how we created the pairs. And this is how the pairs are basically the actions, and the classification, whether it's object or background, is taken into account. So actions, as I mentioned, is taken based on the intersection over union with the ground truth, and the classification is also based on the intersection over union with the ground truth. If it's above 0.7, we assume it as the object, otherwise it's going to be background. And the network is trained by adding these 2 terms, which are basically the actions and the classification loss functions. The loss functions are cross entropy and an average of them is added to each other for training the network in a supervised manner. This supervised learning here, the weights are going to be the initial weights for refining the training using the reinforcement learning by policy gradient. So, which means that action A, action AT here at the current location at state ST is assigned to the network by a conditional probability map, meaning that given the weights of the network at the current step, what is the probability of taking action given the state? And this is how we updated the weights based on the gradient descent. This is the reward function. Based on the action that we take, which is the highest likely action, we get a reward, and this is how we compute the gradient of the weights and update the weights.
So can you go back? Yeah, so I think that, yeah, so this is an important equation, and I think everybody should look at it carefully, and this essentially is doing the policy gradient, and actually the loss, the probability is very similar to what we are doing in the supervised learning, right? The only difference is that we are multiplying with the reward, which is CT, and then we can do that for all the frames from L to uppercase L, and then different iterations they are doing for a particular frame. And so in a way, it becomes pretty trivial, pretty simple doing reinforcement learning using deep learning for this thing. There's nothing fancy about it.
Yeah, the main difference between the supervised and reinforcement learning here is that the supervised, only one action needs to be taken to get to the ground truth. But here, maybe multiple actions needs to be taken, and this reward function somehow forces the algorithm to take the minimum number of actions that leads to negative rewards, meaning that it tries to find the object as fast as possible with the minimum number of actions taken.
And other thing is that in this one, they are going to train this on the real tracking sequences.
Yes. Not the generated patches.
Which we did this.
Yes.
We did the supervised learning.
Exactly.
That's another different.
Exactly.
Real temporal thing going on.
Exactly. Yeah, the temporal information is also encountered here since we are using the location of the previous patch in the next patch as a starting point and follow on. So here this figure shows how the reward is assigned. So assume that we are at time t, and this is our action state history. We achieve a reward of +1 if we find the location of the object, but in case we missed it in the next steps, we'll start getting negative rewards, which are the -1. Okay. There is one last step for the training of this algorithm, which is the online adaptation. The online adaptation, again, is a supervised step, and but there is a difference between this step and the very beginning first step, is that the data that is used here for training the network are basically the outputs of the reinforcement learning algorithm, meaning that the reinforcement learning algorithm is tracking the object online, and at each given frame, it knows the location. It proposes some location for the location of the object, and then we use that location as a ground truth and select some patches randomly around it and try to train in a supervised manner, again, like the first step. But the difference is that the ground truth is not from our data set. It's generated from the reinforcement learning. And it helps to boost the robustness of the algorithm to the appearance changes. The thing is that in case the reinforcement learning algorithm fails to find the object at a given frame, they try to redetect the object using some patches around the object, around the proposed location for the reinforcement learning, and calculate its classification probability of either being background or foreground. So if the reinforcement learning fails here, then they try to search around it and find the actually the very exact location of the object, and then do the supervised again.
Yeah, so I mean, this is done separately for each sequence, right? Because this depends on the particular sequence.
Yes.
And so this learning online, because what previous reinforcement learning or supervised learning was, some training sequences, and you learn that, you get that now, and which you can do fine.
Mm-hmm.
But now, since you have this particular sequence, you want to do even better, that you want to learn from the previous frames where the object has been improved, and the appearance and all these things can vary from sequences.
Exactly. Exactly. This is basically learning during the tracking. So this is a video of their results. They show how the algorithm behaves. So there are two versions of this algorithm, ADNet and ADNet Fast. ADNet Fast is the real-time version, and here is shown in the red. And the green, blue, black, and pink are the other state-of-the-art algorithms. And as can be seen, the method is pretty robust to changing the scales, movements, occlusions, and basically tracking the object very good.
So it doesn't do the rotation, right?
No, not rotation. But here, if you look, it's just the scale because they're zooming, so the scale of the object is changing. The black and pink are missing the object because they're following the previous scale, but they can adapt it. So again, occlusions, everything doesn't affect the algorithm. And this is here showing the sequential actions that are online taking in order to follow the object. So these are basically the actions that are taken at each frame while they're moving the object. Sorry. Okay. Now the results. The first section of the results are the analysis of the actions. Here, basically, they're trying to show how many actions at each frame needs to be taken in order to find the object. Obviously, the less number of the actions shows the better accuracy, the better efficiency. So the proposed method, as reported, in 93% of the times, finds the object in less than 5 actions. So they're taking less than 5 actions at each frame in order to find the object. And here is a second graph that also supporting the previous claim, because the number of stop actions are way more than the other actions, which is basically saying that objects are going to be found at each frame, one after another, without actually a comparable amount of other actions. So there's some basically 4 different baselines of their algorithm that they compared with. The ADNet init is basically the algorithm without that supervised learning step, which is used for initial step.
So what does that mean? Like without supervised, then what do
they use the pre-trained VGG weights instead of training it on the generated state action patches.
Oh, I see. But then they take that model to do the reinforcement?
Yes, yes.
Oh, I see. Okay.
Instead of training it on state action pairs that they generated themselves, they use a pre-trained model. So the weights are for feature extraction at each patch.
I see. But I thought the supervised, so that's the difference between the features, right? So these features would be better if they actually train with supervised.
Yes.
But even these actions,
the features corresponding to the actions, because like pre-trained VGG also can decide extract some good features. But in the supervised manner, if you train it with the supervised, it can be a good match between the features and the actions. What actions needs to be taken given that current?
Yeah. So the first one is VGG, but supervised learning. Right?
The pink one?
Yeah.
No, it's just pre-trained network.
Yeah, but
no
how will that work? Because what I'm trying to understand.
A VGG network pre-trained on
VGG
classification.
trained, right?
Yeah.
But then what about the actions? Like,
so they use the weights before the fully connected layers. They didn't change it, and the fully connected layer is trained from scratch. The weights are random for the fully connected, and then trained from scratch.
They train that.
Yes.
Right? Yeah,
but the previous layers are pre-trained, only the fully connected.
Is that instead of training these feature layers, the other previous layer
from scratch.
This one, then they're just replacing from.
Yeah.
Okay, that's good.
Yes. And the SS here is a semi-supervised learning instead of the supervised learning at the very first step, which means that for some frames, they don't have the ground truth. For some, they have. If that follows by reinforcement learning, and then supervised learning plus reinforcement learning is giving the best results, which is 88% in precision. And here's the success.
So question there. So so what is the reinforcement learning just helping only 2%, right? So
yes,
we can just use supervised learning.
Of course, reinforcement learning is not actually going to help a lot about the precision or accuracy of the network, but it will affect dramatically in the efficiency and real-time tracking of the object. So the point is the efficiency, not the accuracy.
So do you figure out what success?
I forgot. Sorry.
Okay, does anybody know what success of class? Anybody understood? No. Okay, everybody's saying that.
Yeah, okay. I'm so happy. Okay, here are the comparison of results on OTB 100 dataset, and the others are state-of-the-art methods. As I mentioned, and as you can see, the best precision that the network can get is the dotted dark blue curve, which is not basically beating the state-of-art, however, getting a comparable accuracy with a very way better efficiency, as I'll show in the next slide. So this is again the success rate, which we don't know what that is. And yeah, here is the table that I was talking to. So ADNet has two versions, ADNet and ADNet Fast. This is the real-time version of the algorithm. They're not using a GPU. They're processing 15 frames per second, and they're getting a precision of 85.1% as compared to the best real-time current method, which is using a GPU, processing 19 frames per second and getting 77%. So the speed improves dramatically, given that a GPU is not used here.
So what does fast mean? What is the fast?
There is a fast version. Maybe the implementation, they changed it something. Yeah, the theory is the same. They just changed something in the implementation.
Okay. But I'm surprised for that they're not using GPU, right?
Yes, that's basically.
Okay. And then what else do you have?
And but as you can see, like compared to non-real-time algorithms, their accuracy is not comparable. 88 to 90%. They're 2% less than the state of the art.
And then the speed is.
This is not real-time, so the speed is not basically like less than 1 frame per second. And here again, 2.9%. So it's saying that even in the non-real-time version, still the algorithm is faster than the previous state of the art. Okay.
Excellent.
Thanks.
Very good.